Hi. In this section, we're going to dig into matrix multiplication. We've already defined the three fundamental mathematical objects of linear algebra: scalars, vectors, and matrices. We've discussed two operations with them, vector or matrix addition and scalar multiplication. And we've discussed how those two together give us the idea of linear combinations. We're now going to discuss the third operation that we can do with matrices and vectors, matrix multiplication. Before we get into a general definition, I want to talk a little bit more about geometry of spatial vectors, because this helps motivate the definitions that we're going to use and why we might want such operations to be defined in the first place. So if we have a spatial vector, a directed line segment from the origin to some point, again, I'm using the example of vector u equals 1, 3 in a two-dimensional space here. The length of this line would be given using this as the square root of the sum of the individual terms. This is just a standard sort of Pythagorean rule for evaluating the length of the hypotenuse of a right triangle. The x-coordinate is the length of one side, the y-coordinate is the length of the other side. The length of the hypotenuse is the square root of the sum of the squares of the two sides. Right? We visualize this in 2 dimensions. In 3 dimensions, exactly the same rule holds true, that the length of a vector in 3-dimensional space, a directed line segment in 3-dimensional space, is given as the square root of the sum of the squares of each of its coordinates. u1 squared plus u2 squared plus u3 squared, the whole thing square root. Right? This length is often referred to as the norm of a vector, or sometimes more specifically the 2 norm or the Euclidean norm, but norm generally suffices without too much confusion. And the notation we use is 2 vertical lines, 2 vertical bars on either side of the vector. And so double bar u, double bar means the norm of the vector u, and so on. Right? Now, another geometric concept we can talk about vectors is the angle between them. So again, let's take our example of our vector u and vector v that we used for discussing sums and differences, and think about how would we define the angle between these vectors. Well, basic trigonometry also gives us the answer to this problem. If we know the length of one side, right, the length of another side, and the length of the third side, right, and we know how to find this difference of these two vectors, so we can find what that vector is, and if we know what the vector is, we can certainly find its length. Once we have the lengths of all of these vectors, we have everything we need in order to find the angle between them. We use the law of cosines. If this side is A, and this is B, and this is C, the law of cosines is that c squared equals a squared plus b squared minus 2ab times the cosine of the angle between them, represented here by theta. Or in vector terms, the norm of the difference between these two vectors, C, equals the norm of u, A squared, plus the norm of V, which is B squared, minus the norm of U, the norm of V, times cosine theta, AB cosine theta. Right? Since we can, if we know the vectors u and v, we can calculate the norm of u, we can calculate the norm of v, we can calculate the difference and the norm of that difference. The only thing we don't know is the cosine, and we can isolate that by kind of moving these, this term over to one side, this over to the other, giving us 2 norm of u, norm of v cosine theta equals u squared minus v squared minus the norm of v minus u squared. And then final step of dividing both sides by 2 over times the norm of u over norm of v gives us an expression for the cosine of theta. We could take the arc cosine of this, but normally to simplify notation, we define this angle simply by defining the cosine rather than taking that last step. All right, so this gives us a way to do that using norms. Are there other ways to calculate that? Maybe that would be simpler. Well, if we take a look at what this expression is, right, the numerator of this term for cosine theta was this norm of u minus norm of v minus the norm of the difference. Let's expand those out in general terms. The norm of u squared is the sum of all of the individual elements of u squared. The norm of v squared is the sum of all of the individual elements of v squared. And the norm of the difference v minus u is the sum of the squares of the difference vi minus ui for all of the terms in v and u. Okay. This we can actually expand. What is vi minus ui squared? It's vi squared minus 2vi times ui plus ui squared, right? Which we can expand here, splitting each of those terms into individual sums. So each one of these will give a vi squared, a negative 2vi ui, and a negative ui all squared, or a plus ui squared. And then we have to add each of those terms up for every element in the sum, which can be written as these 3 separate sums. If we now look at this, what do we have? We have a sum of all of the elements ui squared minus a sum over all the elements of ui squared. These terms cancel out, giving us 0. We also have a sum over vi squared minus a sum over vi squared. These terms cancel out. And the only thing we're left with then is this one remaining term, a sum over all of the elements of u and v, 2 times vi ui. We can factor the u out and put that out front, 2 times this sum over all of the elements. That allows us to replace the numerator in this definition, which would require us to calculate 3 individual norms, by this sum over the product of corresponding terms. Right? Wherein here I've taken the additional step of canceling out the 2 that appears here and the 2 that is here in the denominator. Right? If I now sort of replace these norms with their sort of definitions as the square root of the sum of the squares of terms, we see that now this ratio that we need to calculate the angle between two vectors actually involves three sums that have the same form. A sum over all of the elements, ui times vi, a sum over all of the elements of ui times itself, a sum over all of the elements, vi times itself. These are all sums over all of the elements of a product of corresponding elements of two vectors, where in the numerator there are two different vectors, and these two terms, the two vectors are both u or both v. This motivates us to define this product, this sum of the product of corresponding entries of two vectors. And we call this the dot product, sometimes called the scalar product. So the dot product or scalar product of u and v is a sum of all of the products of corresponding entries. u1 times v1 plus u2 times v2 plus u3 plus v3 and so on until we reach the end of the vectors. Clearly, this definition requires the two vectors to have the same number of elements, or we wouldn't have have corresponding entries. And we note that the dot product is a scalar. We start with two vectors. The answer we get is a scalar, just a number. With this simplifying definition that the dot product of two vectors is this, we can then write this, both the norm and the cosine of the angle, the norm of one vector or the cosine of the angle between vectors, in terms of this dot product. The norm of a vector is the square root of the dot product of a vector with itself. The cosine of the angle between two vectors is the dot product of those two vectors divided by the lengths or the norms of those two vectors, which in turn are defined in terms of the dot products. Right? These properties, that both the length of a single vector and the angle between two vectors, or more specifically the cosine of the angle between two vectors, can be defined in terms of dot products, make this an incredibly useful operation in many, many applications. Many of you have probably come across the dot product in other classes, either in other math classes, in physics classes, or so on. All right. Now that we have the dot product under our belts, we're able to now define a more generalized product between matrices of certain types. And we're going to use the dot product as part of our definition. Right? We're going to think about a product between two matrices where the answer is another matrix, and the matrix is defined such that the ijth element of the product, that is the ith row, the element in the ith row and jth column of the product, is obtained by walking along row I of the first matrix and column j of the second matrix, multiplying corresponding elements and adding them up. That is, taking a dot product of those of one row and one column. I think the best way to sort of really visualize this is by going through an example. We start with the first row of A and the first column of J, and that gives us our first entry 1, 1 in our matrix. We add the corresponding entries, 1 times 4, multiply corresponding entries, 1 times 4, 0 times 6, -1 times 5, and add up the results. Right? This gives us 4 plus 0 minus 5 for an answer of -1 for that particular product. We then do the same thing with the, actually let me use the same color for our second product. Actually, I will change colors, sorry. Change to green. We again start with the first row of A, but now we move on to the second column of B. We multiply the corresponding entries. 1 times 2, 0 times 0, -1 times -2. And add up the corresponding entries. The result is 2 plus 0 plus 2 gives us 4. We then continue this starting with the second row of A, second row of A, first column of B gives us entry 2, 1 of the product. So second row, first column in the product. 2 times 4 plus 1 times 6 plus 3 times 5, which is 8 plus 6 plus 15, or 29 for that entry. One more entry in the product we get by, again, starting with the second row of A, but now using the second column of B for entry 2, 2 in our product. 2 times 2 plus 1 times 0 plus 3 times -2, which is 4 plus 0 plus -6, or -2. We take a row of the first matrix and multiply it with a column of the second matrix. We do that for all possible rows of the first and all possible rows of the second. Clearly, in order for this to work, the number of elements in the rows of A and the columns of B have to be the same. Right? If A has M rows and R columns, then B has to have R rows and N columns. We say that the inner dimensions have to match. The number of columns in A, which is the length of the rows, and the number of rows in B, which is the length of the columns, have to match. If they didn't match, we wouldn't have corresponding entries. Okay. In the product, the answer has the same number of rows of A, because that defines the row of the product, and the same number of columns of B, because that defines the column we use defines the column of the product. This means that if A was an M by R and B was an R by N, the product ends up being M by N. So the inner dimensions, the number of columns of A and the number of rows of B have to match. And when we take that product, that dimension kind of disappears. What we are really doing is in each step, we are taking the dot product of a row of A and a column of B for every entry in the product. We might define it in this way. If we define A as a number of rows, where each row is a vector that I'll call a row I, and we define B as a set of column vectors, B1C, B2C, and so on, then each element Cij, the ith element of ith row and jth column of C, comes from taking the dot product of AI row and BJ column. This type of multiplication can be confusing. A lot of students have a little bit of trouble with it when they first start doing it. You learn how to be comfortable with matrix multiplication by practicing. Do practice. There will be practice on the homework. And there will be some worked examples to look through to give you that practice, and it will come to you. While many students have trouble with it at the beginning, in my experience, almost every student is able to master it with a little bit of practice put in. All right? Now, for vectors, well, vectors really can seem a lot like matrices, and they can be treated in matrices of a particular type. In particular, matrices that only have a single row or a single column look really a lot like vectors, right? And we're going to see that they behave almost identically, right? That is, anything that you would like to do with a 1 by n row vector or n by 1 column sort of vector, you can do sort of treating them like matrices largely, all right? Now, because of how the rules of matrix multiplication works, though, and how matrices have to be exactly the same size to work with, when we're thinking them of as matrices, vectors as matrices, we need to make a bit of a distinction between a row vector, where we orient things as a row, and a column vector, where we orient things as a column. Right? This distinction is mostly important just to be clear about the rules of how we multiply things using the laws of matrix multiplication. Because from a conceptual point of view, if we think about a spatial vector, if we think about a vector corresponding to a list of elements, an ordered list, whether we write them as a row or whether we write them as a column is irrelevant. The only reason the row and column orientation matters is because of the rules of how we work with matrices, not with vectors, per se. It's helpful to have a way to sort of just easily switch between column form and row form as needed. And the transpose is an operation we define that lets us do that. The transpose is an operation that simply takes the rows of a matrix and makes them columns, and the columns and makes them rows. When applied to a single row vector, it creates a column vector that looks exactly the same, and vice versa. we use the notation of superscript T for the transcript. And so column vector U is simply the transpose of row vector U. Row vector U is simply the transpose of column vector U. With this sort of definition, we can actually now write the dot product just as a matrix product. We're going to choose a standard where a vector is treated as a column vector by default. Any vector, if we want to write it down, we'll sort of assume that in the language of matrices, it's a column vector. That is, a vector of length n is sort of interchangeable with a matrix that has n rows in one column. Right? The transpose of that vector is then a row vector if we need it. And if we want a row vector, we use the transpose because we always assume a vector is a column. So U is assumed to be a column vector. U transpose will then be a row vector. With that set of a standard, what would V transpose U look like? It's a row vector of elements V and a column vector of elements Ui. We can multiply this matrix that has one row with this matrix that has one column. Because there's only one row on the left and only one column on the right, we end up with a 1 by 1 matrix, which is essentially a scalar, only one answer. And what is that answer? It's the answer we get from walking along the row and the column, multiplying corresponding entries, and adding them up. V1 times U1 plus V2 times U2, and so on. That is the dot product. Right? So the dot product is simply V transpose U. One of the nice things about this is actually we don't even really need the concept of the dot product anymore. Or rather, we don't need a specific notation of a dot product anymore. The concept is really, really helpful, related to length, related to angles, and so on. But we don't actually need to have this special notation of a dot product. We can always simply use matrix multiplication to represent the same thing. Some people still like to use the dot product notation, and there are applications where kind of extensions of more generalized inner products where this can help. And others like to sort of be more operating purely in a matrix algebra space and prefer to use this notation. It's good to just sort of make sure that you internalize that this product and this product mean the same thing. We've kind of defined the transpose, or we've, in the context of just a single vector. The transpose can be applied to matrices more generally also. The definition is the same. It's an operation that converts the rows of a matrix into columns and the columns into rows. We don't need that extra into there. And well, for row and column vectors, this is really a trivial case. We just sort of write it as a row instead of a column. We can generalize this to any matrix. If we start off with a matrix where we think about it as existing in rows, the transpose, we just take every one of those rows and write it as a column. If we think about a matrix starting as columns, we take either all of those columns and write them as rows when we want to make the transpose. It doesn't matter which one we do, we will get the same answer. If you take a matrix and you take the rows, and write them as columns, or you take the columns and you write them as rows, you get the same result. Okay. Important to remember that because we're taking rows and making them columns and vice versa, when we take the transpose of a matrix, we change its size. If we start with a matrix with m rows and n columns, or m by n matrix, its transpose switches those. The number of columns of the original matrix becomes the number of rows of the transpose, and vice versa. Right? Okay. That really defines all of the key operations: matrix multiplication, and matrix transpose. I now want to spend a bit of time just talking about some special cases and some extra notation that you'll see that applies specifically to certain classes of matrices. For arbitrary matrices A and B, the product is often not the same size. Remember, the inner dimensions of A and B have to match, but they disappear. And so the product is an M by N matrix, where A was M by R and B was R by N. In general, the product will be of a different size. But if A and B are square, what we mean by a square matrix is a matrix that has exactly the same number of rows and columns, and they're of the same size, then the product will be well defined, and the product will be the same size. If A is N by N and B is N by N, the inner dimensions match, so we can multiply them. It disappears, and so the answer is N by N. We get a matrix of the same size. Because of this, when we have square matrices of the same size, we can multiply them in as many times as we want. We can take 3 square matrices and multiply them together. We get a matrix of the same size. We can take 4 square matrices of the same size, multiply them together, and we'll get a matrix of the same size. We can take 1,000 square matrices of the same size, multiply them together, and get a square matrix of the same size. One really interesting result of this is that we can define powers of square matrices, at least initially, for positive integer powers. Right? That is, we can define A squared, meaning A times A cubed, meaning A times A squared, or A times A times A to the 8th, meaning a product of 8 copies of A multiplied together. The rules of sort of how the exponents add together work in a similar way as exponents of scalars. A to the 8th equals A to the 4th times A to the 4th, or A times A to the 7th, and so on. These powers are well defined for any square matrix. They do not make any sense if we do not have a square matrix. Actually, in general, if a matrix isn't square, we can't multiply it by itself because its number of rows doesn't equal its number of columns. Okay, that's one special case. Another really special kind of matrix is something called the identity matrix. The identity matrix is a square matrix that has ones for all of the entries on the diagonal. That is, the entries where the row and the column is the same. Entry 1, 1, entry 2, 2, 1, 1, 2, 2, 3, 3, and so on. But has zeros everywhere else. We can define such an identity matrix for any square matrix. 2 by 2, 3 by 3, and n by n. And if we need to, we can use a subscript so that we know which identity matrix we're talking about, which size, although very often we just use I And it's assumed that we know the right size, or that we're using the right size for things to make sense for our problem. One of the really interesting things about the identity matrix, and this is why we call it the identity matrix, is that as long as the product is well defined, right, as long as the size of the identity matrix is the right size, multiplication does not change the matrix. I times A equals A, B times I equals B, as long as we're using the right size I. It's this property which is exactly why we call it an identity matrix. The identity matrix behaves like the scalar 1. You multiply 1 by something, you get the same answer. You multiply a matrix by I, you get the same thing. Right? The number 1 is sometimes referred to as the multiplicative identity for scalars. The identity matrix is the multiplicative identity for matrix multiplication. Another special case that we're really not going to be getting into right now very much, but we will be getting into later, so I'd like to just sort of prime the pump a little bit by introducing the concept of it. If the identity matrix behaves a lot like the scalar 1, it's the multiplicative identity, we might think about whether there's other things that we can take lessons from scalars. In scalars, for everything other than 0, we have something called a multiplicative inverse. A multiplicative inverse is a number that when we multiply it by the number we started with, we get 1. We get the multiplicative identity back. X times y equals 1 means y equals 1 over x, or y equals x to the negative 1. The inverse of x, the multiplicative inverse of x. Or x equals 1 over I, x is the multiplicative inverse of y. We can do this for every scalar other than 0. We might ask the question, can we do something similar for square matrices? Is there such a thing, a multiplicative inverse, treating the identity matrix like 1? That is, if A times B equals I, can we define B to be the inverse of A and A to be the inverse of B? It turns out that we can do this, but we can't do this for every square matrix. For some square matrices, there is no matrix that we can multiply it by to get I. But if we can find such a matrix, then it has all of the same properties as a multiplicative inverse. For the time being, just sort of be aware that you may sometimes see this notation of A inverse, and this is sort of what it means. We'll be digging into this idea much more a little bit later in the semester. Another special matrix you might sometimes see is the 0 matrices. These are matrices that have zeros everywhere. 0 matrices don't have to be square, right? We can only define an identity matrix for a square matrix because we need to have kind of this well-defined diagonal property. For 0 matrices, we're just filling the whole thing with zeros, so there's no reason that we can't make any matrix, any size matrix, a 0 matrix. Again, we can use subscripts to specify what 0 matrix we're talking about, a 2 by 2, a 3 by 3, a 3 by 2, a 2 by 4, and so on. But again, we very often just use 0, where we assume that the right size is well defined by the problem. Right? As long as the matrix is the right size so that addition makes sense, Addition of the zero matrix to any matrix doesn't change that. We might say that the zero matrix is the additive identity in the same way that zero, the number zero, we can add to any scalar without changing it. Just as we can multiply the scalar 0 by a scalar and we always get 0 as an answer, if we multiply any matrix by a zero matrix, we'll get a zero matrix. The size of the zero matrix has to be appropriate to be well defined. It's important to note, however, that the size might be different. And because the size might be different, the answer of the zero matrix that we start with may not be the same size as A. It might not be the same size of the zero matrix we started with, and so on. But it will always be a zero matrix. Okay. Now, when we think about a vector as a column matrix, a column vector, we can then start thinking about multiplying a matrix by a vector, right? And in particular, if a vector is an n by 1 column matrix, then for any matrix that is m by n, that is any matrix that has the same number of columns as our vector has elements, we can define a product A times X, matrix A times column vector X. The answer, because we start with an m by n matrix, and the inner dimensions have to match and then disappear from the product, the result is an m by n matrix or another column vector. So the product of a matrix and a column vector gives us another column vector, but perhaps of a different size. If A is not square, we will have a different size vector as the answer. Right? We can also, if we use the transpose of a vector, so we're dealing with a row matrix, we can always define a product of a row matrix or a row vector by a matrix. And in the same way, when we start with a 1 by m vector x and a m by n matrix, inner dimensions match, inner dimensions cancel in the product, they leave us with a 1 by n row vector as an answer. The second form is seen much less frequently. This first form is very commonly seen. A very, very important thing to make sure that you sort of get familiar with. We are going to see expressions in this general form, AX equals B, matrix times vector equals another vector, over and over again throughout the class. Right? The reason we are going to see this over and over again is something really special happens when A is a matrix of constants and X is a vector of variables. So let's take a look at that. Start with an example, a 2 by 2 matrix and a 2 by 1 column vector. The rules of matrix multiplication say that how do we calculate this product? We take the first row and we multiply it by the first column. multiply corresponding terms and add them. 2 times x plus 3 times y. We then do the same thing for starting with the second row. And we only have one column for here, so we use the same column. 1 times x plus negative 2 times y is x minus 2y. The result, this product, looks exactly like the left-hand side in a system of equations. Right? I could write it as a system of equations. 2x plus 3y equals 7. X minus 2y equals negative 5. Right? Well, this equation I could write as a vector equality. If I can write the left-hand side as a vector where I have both of these, I can equally write the right-hand side, 7 and negative 5, as a vector. And this system of equations and this vector equality, the vector where I have equations as the two rows on the left-hand side as numbers on the right, are exactly equivalent. These two representations mean exactly the same thing. But this representation, we've just seen, can be represented as a product, which means we can write this as a product of a matrix and a set of variables, which allows us to write this system of equations in the general form of AX equals B, where A is a matrix, X is a column vector of variables, and B is a vector of constants corresponding to the right-hand side of the equations. This is an incredibly, incredibly important point that we will be, and mode of representing linear systems that we will be using throughout the semester. We will have lots of practice in how these work and how we translate between these, even in some worked examples that I'll present in a follow-up video, as well as in homework. All right. Just to sort of go through the key points with this, when A is a matrix of constants and X is a vector of variables, then AX equals B is a system of equations. I should highlight also that B is a vector of constants typically. The number of rows in A corresponds to the number of equations in the system. The number of columns in A corresponds to the number of variables in the system. The product AX gives us the left-hand side, the side that has all of the variables and sums of linear products of constants with variables, and B corresponds to the constants on the right-hand side. All right. That wraps up our kind of conceptual lectures for this second unit, an introduction to the matrix product. There is a set of worked examples in an accompanying lecture for this section, and there is also one more video where we sort of expand the lecture, the language of linear algebra, to consider abstract work with expressions that involve matrix and matrices, vectors, scalar multiplication, addition, and so on. Thank you and goodbye.